Greetings, my name is Stefan Sorger. I'm an instructor for data analytics and data mining courses. I'll be taking you through some basic steps of preparing your data for data analytics projects. We've made every effort to ensure accuracy and relevancy of the content. Nevertheless, we cannot control how the information is being used, so we assume no liability for the use of this information. In this presentation, I'll take you through the steps of preparing your data for data analytics projects, from collecting the data all the way to partitioning it for certain types of analytics projects. We start with collecting the data and laying it out. In this case, we've collected real estate data for the area in the United States defined by zip code 94028. The area is located in the San Francisco Bay Area and consists of fairly expensive homes. In this case, we pulled the data from multiple data sources, which required us to make sure the units were all the same, as well as the sequence of the columns. Note that each row represents one record of data. In our case, each row represents one home. The very first row should be what's called the header row, which consists of labels for each column. The columns represent variables. In our case, our real estate data has several variables. The first variable is price 1,000, which is defined as the sales price of the house multiplied by $1,000. The second variable is size square feet, or the size of the livable space in the house in square feet. The third variable shows the size of the building lot in acres. The fourth variable indicates the year the home was built. The fifth variable shows the number of bedrooms. The sixth variable gives us the number of bathrooms, and the sixth variable gives us the neighborhood of the home, which can be one of three categories: Central PV, Ladera, or Westridge. Because we have a mix of data, we'll likely want to use data frames in R to capture the data. In this slide, we discuss variables for data analysis. In terms of the number of explanatory variables, we never want to have more than we need due to the complexity of dealing with more variables. Of course, we need at least one data point per predictor variable, but that would not be a very robust data set. In general, we recommend collecting at least 10 points per predictor variable. R has multiple data types, including different numeric types, logical, and character variables. What it does not have is categorical data types, such as ordinal and nominal categorical variables. To accommodate ordinal data in R, we often employ a hack where we model each level numerically, such as 1, 2, and 3 for low, medium, and high, respectively. But that won't work for nominal data. We recommend using dummy variables for nominal data. In dummy variables, we select one dummy variable for each potential value. In our case, we have our neighborhood variable with 3 potential values. So we created 3 dummy variables, one each for 3 potential values. Central PV, which is assigned 1 if the property is in the central PV neighborhood, and 0 if it's not. Ladera, which is assigned either 1 or 0, and Westridge, which is assigned either 1 or 0. Observant viewers will note that our scheme is redundant. If the property is not in central PV or in Ladera, there's only one alternative, which is Westridge, and you'd be correct. That's why we need only n-1 dummy variables to represent n potential values. This slide shows the schema as expressed in the data. We start with 4 columns, our original neighborhood column, along with 3 columns for our dummy variables. We remove the original neighborhood column because it is being replaced by the dummy variables. We can also remove one of the dummy variables due to redundancy. We're left with 2 columns, nay central PV and nay Ladera, both of which are logical variables which can be either 1 or 0. In our case, the first home gets a 1 in the nay Ladera column, so that's where it's located. With the data set ready to go, it's time to read it in. We start by double-clicking on the R icon to launch it, and we arrive at the R console interface. We recommend setting up a working directory, Setting up a working directory tells R where to go to look for R files. That way, you only need to specify the file name, not the entire file path. If you've not done so already, save the data in comma-separated value format known as CSV. We then read in the CSV data using R's read.csv function. Because this dataset includes multiple types of data, we recommend saving it in as a data frame, which is designed to hold multiple types of data. We can invoke the summary function to get summary statistics on the data. The summary statistics shows us minimums, maximums, medians, and means, among other things, for each variable in the data. We check the data to detect any potential problems, such as outliers. One good check is to compare the means and medians for important variables. When they differ, as they do here, it typically means we have a large value somewhere in the data pulling the data upwards. In our case, we know we have some high-priced homes in excess of $16 million, priced significantly higher than average, so we're not surprised by this result. It can be useful to also check the minimums and maximums for each variable and check the reasonableness of each. For example, a min and max of 2 and 6, respectively, for bedrooms seems reasonable. Had we seen a max value of 42 for bedrooms, we would have been suspicious. We now need to check for missing data. For small data sets, we can visually check for blank spaces. For larger data sets, we can use the summary function to check for zeros and non-zero variables. For example, we should not see zeros for variables such as price and size. We face several options when encountering missing data. The best option is to avoid it. When developing surveys, make sure each survey question should be mandatory, then delete the question in the survey if it is not. The second option is to ignore the problem. This only works if you have a very small percentage of missing data. The third option is to delete the problem. In this case, we just delete the record with the missing data. This third option is limited because we have potentially changed the data set. The fourth option is to replace missing data with representative data. Typically, we replace the missing data with means or median values of the other data of that variable. R calls missing data NA, or not available. NA values are a problem in R. For example, we cannot compute statistics in data with an NA in it. Luckily, R gives us two useful functions to address NA values. The first is na.rm, which strips NA values before computations. The second is the is.na logical variable, which flags as true if R detects an NA value. As an example of na.rm, the mean function includes an optional na.rm parameter, which strips or removes any NA values in the data before computing the mean. As an example of is.na, we can write that if any data file element is an NA value, that will replace that value with 0. In the next slide, we'll show an example of what to do when we encounter missing data. We see a revised data set with a blank value deliberately introduced into the first bedrooms variable. We call this modified data set realDataNA.df to emphasize that it has an NA value in it. We decide we want to keep this data record and that we want to replace the missing data value with the mean of the remaining data. In other words, we'll compute the average number of bedrooms for the zip code and then substitute that average value for the actual value it should have been. In the R code at the bottom of the slide, we start by reading in the data and placing it in the data frame realDataNA.df. We tell R to compute the mean number of bedrooms in our realDataNA data frame, but it can't because the NA value embedded in the bedrooms variable. So we revise the mean function to include the NA.rm parameter telling R to compute the mean using the remaining values. In the next line, we tell R that if the data has NA values, checked by the is.na function in the bedrooms variable, to replace those NA values with the mean value for bedrooms, computed using the remaining values. We then double-check our work by computing the mean number of bedrooms in the modified data frame, and we arrive at the same mean value as before. Therefore, our efforts have been successful. From time to time, we'll find it helpful to get samples of data, so we'll show you how to get a sample of an original data set. For example, for large databases, we find it easier to work with representative samples rather than the original data. First, some algorithms are limited to the size of data they can handle. And second, larger data almost always takes longer to process. The syntax for sampling is shown on the slide. We start with the word sample and then place the parameters of the function in parentheses. The parameters include the data x, whether the sampling should be done with replacement, and the probability weights for the samples. The function is best explained by example, so let's get to it. For our example, suppose we want to get 3 sample rows of data from our real data data frame. We would ask R to give us the row names specified by using the term row.names. We would also specify the data frame, which we called realData.df, and the number of samples, which we declared as 3. We then put the output of the function into a variable we arbitrarily called samp and printed out the results. You can see the results in the slide. They appear to be pretty random with no common values apparent. How did you know how to do that? The answer is by following the instructions. Whether we're following a new recipe in a cookbook or filing a tax return, our goal is to find the instructions on doing the task and then follow them step by step. In the case of the number of samples, I searched the R help files for instructions on sampling, and it gave me the file shown. Each help page shows the description of the R function, the usage or syntax, the arguments you can use with it, and very clear examples. I then just followed the instructions to execute the function. Sometimes a random sample is not what we want. Often we want to overweight a particular variable or situation of interest, especially if we're interested in that particular situation. To oversample, we can use the if-else function. The if-else function tests for a certain condition, and the user specifies what R should do if that condition exists, i.e. if it's true, and what to do if it's false. For example, suppose we're particularly interested in homes built in 1960 or newer. We would then use the if-else function to test for the year of construction being built greater than 1959. If the home was built after 1959, we want to include it in our sample, hence the large 0.9 value in the R code for the yes branch of the if-else decision function. If the home was built earlier, we do not want to include it, hence our 0.01 value for the no branch. We can verify in our printout at the bottom of the slide that the sample only includes homes built after 1959. Our final topic in this presentation is data partitions. We partition data for supervised models such as regression or classification so we can validate the model we build. Supervised models have a dependent value, also called a response value, which we wish to predict with predictive or explanatory variables, and we want to assess the validity of our model. We can't validate the data with the original data because that would lead to confirmation bias. So instead, we leave some portion of the data out and use it later to validate the model. That's called partitioning the data. We often allocate about 60% of the data to build the model using what's called the training data set. We use the rest of the data to validate the model we built. Using a validation data set alone is sufficient, although occasionally we employ the use of a holdout or test data set. To partition the data, we use the sampling techniques we just covered earlier. For example, say we want to partition the data into two sets. 60% of the data would go into a training data set, and 40% would go into a validation data set. In that case, we take a 60% random sample of the original data frame to get the training sample. Here we get the rows corresponding to the 60%, and then get the data corresponding to that set of the so-called training rows. We call the resulting training data train.data. We then take the remaining rows and declare those to be the validation partition rows. Just as before, we get the data corresponding to the remaining rows as the so-called validation rows or valid rows. We call the resulting validation data valid.data. Again, we use the partitions for supervised data analytics and data mining problems. In this video, we covered data collection, where we saw an example of gathering data from multiple sources. We then covered the data layout and the types of variables making up the data. We discussed how to use dummy variables to express nominal categorical data. We covered typical processes in R regarding data, including reading the data into R, assessing the data for potential problems, and addressing missing data, if any. We concluded the video by showing how to take samples of data and provide an example of sampling, in this case partitioning data into training and validation data sets for supervised learning. Thank you for attending. If you enjoyed the video, please subscribe to the channel.